Let's consider this following problem. Consider a solenoid with n turns per unit length carries a current I. Assume the magnetic field is parallel to the solenoid inside of it and zero outside. Find the B field inside the solenoid, assume it's uniform. Be sure to draw the curve over which you will apply Ampere's law. All right, so this is an Ampere's law problem. Let's draw a solenoid, all right? And we'll draw a cross-sectional part of the solenoid. So we're going to imagine basically that the B field is that the current is pointing inward in one direction over some length, let's say L here, okay? And then it's coming out. And I'm going to assume the B field is going to be moving in this direction. If you want to check, this is actually the right direction of it, as it curls in this direction. Okay, so that's my B field, and it's going to B equals 0 outside. There's no B field outside of it. All right, so I'm going to draw my Amperian curve. There's my Amperian curve. Okay, and so it's going to consist of 4 sides. Basically, I'll call this basically 1, 2, 3, and 4. All right, and so let's write down Ampere's law. This is basically B over some closed curve C. That's the C right here. dl is equal to mu 0 I C, which is the current that flows through the surface C. Okay, actually the current that flows through the surface S defined by the closed curve C. All right. Okay, so let's go ahead and do this, right? So there are 4 segments here, so we're going to break this down to 4 different segments. Okay, 1 B dot dl plus integral of 2 B dot dl plus integral of 3 B dot dl plus integral of 4 B dot dl. Okay, so there are 4 segments here, right? And again, this is always the easy part. This is usually the hard part. Okay, though this might be a little different in this case, right? So let's go through each one of these things. So first thing, there's no B field outside the solenoid, so this is just going to be 0, right? Because B is 0. Okay. Likewise for 2 and 3, okay, there are 2 possibilities. The first is you're outside of it and there's no B field, that's 0. The second piece is that you're perpendicular, right, to the direction of the B field, and because you're doing a dot product in this case, the dot product of 2 perpendicular vectors is also 0. So no matter what, this is going to be 0, that's going to be 0. So you're just left with number 4 right here. Okay, so let's go ahead and do number 4. So this is going to be basically B dot dl. Okay, the B field is pointing in this direction and it's uniform everywhere because that's the assumption. And dl is just basically pointing along this. So this is just, these are parallel here. So it's going to be integral of B dl. B is a constant, so that's B dl. So this integral along this side is just times B times L. Okay, now this is going to be equal to what? The current that flows through it. So it's mu 0 times the current. So how much current is flowing through each wire? Well, there's I, but there are 1, 2, 3, 4, there are n-ish wires, right? Now, the where does it say here? There are n turns per unit length here, right? And there are L lengths, so it's going to be n times L. These are the number of turns. Okay, and so we have this set up, so now we're done. So we're basically left with B is equal to, the L's will kill each other, mu naught n times I. And that is the answer for that one.